Today, on how it's made. Glass bottles. Clearly fascinating. Hacksaws. We're off to a tool factory that's a cut above. And goalie masks. Making them is a face-saving endeavor. Whether they're colored or clear, glass bottles and jars are green. No trees die to make this eco-friendly packaging. Glass is made of natural ingredients that are abundant. You can recycle glass endlessly, and making it uses less energy than producing metal or plastic. The recipe for glass combines about half a dozen natural raw materials, but the main ones are silica sand, soda ash, and limestone. Silica sand usually makes up about 45% of the batch. The soda ash helps melt the silica evenly. It comprises about 15%. A limestone content of about 10% makes the finished glass more durable. They combine these ingredients with recycled glass called cullet. The factory's equipment feeds precise amounts of the materials into a furnace. Over a full day, the fiery heat, 1500 degrees Celsius, melts everything together, producing a gooey liquid that's the consistency of honey. The molten glass pours out of the furnace. Shears cut the flow at precise intervals to produce cylindrical gobs. Each gob is the exact amount required to make one bottle or jar. They drop to a device called the scoop. The scoop moves them to troughs that feed them to jar and bottle forming machines. A gob of molten glass goes into a preliminary mold. In a matter of seconds, it comes out as what's called a parison, a miniature version of the final bottle. Each parison then moves into a blow mold, the cavity of which is the shape of the final bottle. The equipment blows compressed air into the parison, stretching the glass outward towards the wall of the mold cavity. This process creates the final bottle shape and hollows out the inside. These are amber-colored beer bottles. The color is produced by adding small amounts of iron, sulfur, and carbon to the glass mix. The factory uses a similar manufacturing process to produce other types of bottles and jars. In this run, the company is making 375 milliliter wine bottles out of clear glass. This run is producing 375 milliliter liquor bottles, also out of clear glass. But this mold has a special feature, a recessed insignia on one of the walls, which produces a raised insignia on the front of the bottle. After the bottles leave the forming machine, they travel through flames. Otherwise, they would cool down too quickly and crack from thermal shock. A loader now gently pushes the bottles into what's called an annealing layer. The bottles cool at a controlled rate as they move through the layer. This releases stress from the glass gradually. As the bottles exit the annealing layer, a sprayer coats their exteriors with lubricant. This enables them to move smoothly through the rest of the inspection and packaging line. The bottles now line up in single file to head into the automatic inspection station. As the machine spins each bottle, cameras and probes check for imperfections such as cracks or bubbles. The inspection equipment then examines the top to check dimensions and ensure the threads for the screw cap are molded correctly. Before shipping, a worker does a final visual inspection. The proportion of cullet in glass can be as high as 90%. Cullet melts at a lower temperature, so for every 10% of cullet in the mix, the factory uses up to 2.5% less energy to produce its glass. Now that's an incentive to recycle. The world of saws is made up of many marvelous tools. Big saws and jigsaws, handsaws and bandsaws, backsaws and hacksaws. They all have their specific purpose. Hacksaws are chiefly for cutting metal or other tough materials. So what keeps hacksaws on the cutting edge? Hacksaws come in many shapes and sizes. Companies make hacksaw blades out of a wide range of steel alloys. Here, a thin band of steel feeds into a machine that cuts it into blanks 25 to 30 centimeters long and 1.3 centimeters high. Workers load 300 blanks at a time into a jig. They lightly hammer them to compress them into a block for easier cutting. They then feed the block into a machine called a mill grinder. It cuts teeth into the upper side of the blanks. A water-based lubricant washes away the metal particles. This hacksaw model has a 24-point blade, which means there are 24 teeth to every inch or 2.5 centimeters. Workers use an ordinary paintbrush to remove any metal residue. The quality control department inspects each blade for flaws. Then it's off to the next phase. A separator detaches each of the 300 blades, aligns them, then sends them through a setting machine. The machine bends the teeth to either side at a slight angle. This is called offsetting. It'll enable the blade to clear away particles as it saws, preventing it from jamming. Now it's time to harden the teeth. The factory does this by heat treating the metal. A worm gear aligns the blades to enter a heating coil. In this process, the electromagnetic heating coil heats the teeth to temperatures as high as 1200 degrees Celsius, depending on the type of metal. This takes no more than 2 seconds. After the blades exit the heating coil, the surrounding air cools them down over the next several hours. This phase is called air quenching. The blades are now ready for printing. An offset printing press applies ink to raised lettering on a cylinder. That cylinder transfers the ink to strips mounted on another cylinder. These strips then print the company name, the blade length, and the number of teeth per inch on the side of the blades. Now a machine inserts the blades in groups of 5 into slots called fingers. The fingers rotate the blades and place them on a conveyor belt. The machine raises the blades and tapes them together at one end. This makes it easier to transport them to another part of the factory, where production continues. Next, the hacksaw's frame, the component that holds the blade. Workers place the frame components in a jig that's positioned on a rotating carousel. A robotic welder fuses the components. A press punches 3 holes in the handle for attaching a foam or plastic grip. Workers fit the 2 halves of the grip in a sonic welder that fuses them using high-frequency sound waves. The sound waves create friction at the seam. This generates enough heat to melt the parts together. Now the frame is ready for the blade. An automatic device tightens a wing nut to put tension on the blade. A final quality control check. With each randomly selected blade, the testing machine cuts through a block of stainless steel. The machine performs this test 6 times per blade. Then the computer calculates the average number of strokes. If that average falls within the norms for this particular model, the batch gets the thumbs up. Keeping those thumbs, of course, clear of these sharp tools. Goalie masks are all about putting up a tough front. It's not just their protective shell and cage, their wild paint jobs are designed to intimidate. Incredibly, back in the 1960s, the first masked goalies were ridiculed by fans who viewed the masks as a sign of weakness. It was a case of adding insult to injury. Today, these masks allow the goaltender to play it safe, so they're far less likely to be sidelined by a serious injury. They start with a plaster mold of an average Joe. They plug the mouth hole with plasticine. This ensures that the mold won't spring any leaks while they fill it with plaster of Paris. They let it dry for half an hour. Then they pull off the initial mold to reveal the solid impression. They press plasticine onto strategic areas. This mimics the foam safety guards that cushion every mask. The final result is called a plug, and it will be used to make a 2-part compression mold. After applying a black sealer, they polish it smooth, eliminating imperfections that would be visible on the mold they're going to make from it. Over at another station, a worker in protective garb unrolls fiberglass fabric. He cuts and layers sheets of it, then draws patterns onto the top one, spacing the shapes closely together to minimize waste. The goal is to score 100 goalie masks from one roll of material. Using a disc cutter, he slices through 25 layers of the fiberglass fabric. Then he stacks various composite fabrics, several of the fiberglass ones, and patches of Kevlar for reinforcement. Kevlar can absorb so much impact, it's also used to make bulletproof vests. He places more fabric over the Kevlar. He spreads an epoxy resin onto each layer. He drapes them over a mold that's been made from the plug and smooths the material to eliminate air pockets as he continues to layer and glue. He's laminating all the pieces together to form one. He trims away the ragged edges and then places the inside portion of the mold into the outside one. The wet fabric is now sandwiched between the 2 mold pieces. He lowers a 1-ton press to compress the layers of fabric as the resins between them continue to form a bond. He adds some clamps to keep things tight. After 20 minutes, he pries the laminated fiberglass shell out of the mold. This is one very tough shell. It's the raw form of a goalie mask, but it still needs a lot of work, so it's over to the trimming and grinding station. He places a trim jig over the shell. Using a high-speed router, he cuts an opening for the cage. He slices off the flash with a disc grinder. And then he sands and grinds the edges. He drills holes to attach various fasteners. Then he carves out larger holes for ventilation and to reduce the mask's weight. Coming up next, watch as the paint pros go to work on these shells. The makers of Goalie masks have turned safety into an art form. The Goalie mask has become a canvas for some very bold designs and colors. It's a kind of psychological tactic to intimidate the other team, and it also scores points with the fans who like the cool paint jobs. They prep the mask by roughing it up with an orbital sander. Then they pour a sealer into a container. The technician wears a charcoal respirator because the emissions are toxic. He adds the activator solution and a reactive reducer and stirs the sealer together. Then he sprays the sealer mix onto the masks. The finish will cure and harden as the chemicals in it generate their own heat. Next, this system stirs up some hot hues automotive paint as the technician sprays a vivid gold base coat onto the masks. Computer graphics created with SignLab software are sent to a plotter that cuts out adhesive vinyl paint masks. He pulls away unneeded vinyl around the stencil, a process called weeding. Then he presses the vinyl stencils against the Goalie mask and peels off the paper backing. Applying a stencil to the crown is tricky because the surface is curved with ridges, so it doesn't lay flat. He lifts and cuts the pattern with a utility knife and then straightens it out. This mask is starting to look pretty impressive. But they cover the whole thing with white paint. It's a temporary cover-up. This process is all about layering patterns and color. They apply more vinyl shapes. And then, using a pressurized paint system, they spray everything bright red. Next, an artist airbrushes some shadowing onto the now barely visible image of a leaf. He peels away some of the paint mask vinyl. And it's time for a really neat effect. He sprinkles the surface of the mask with water. Then he mists it with paint, and the water droplets catch the paint. He blasts it with a heat gun. The water evaporates, but the paint dries in droplet form, giving the mask a frosty look. He airbrushes a drop shadow around some lettering, dispensing with the usual safety gloves for this detail work. And now, all is revealed as he peels away the vinyl. The Goalie mask is showing its true colors. But wait, a little touch-up job is needed. He traces the pattern onto see-through paper and then transfers it onto Bristol board. He cuts it out with a utility knife. Then he aligns it with the shape on the mask and precisely airbrushes around it to make the smudge disappear. With the final clear coat, this mask has visual impact. It makes a colorful statement. And now it's time to put all the pieces together. She screws on the stainless steel cage and applies a little glue to reinforce the adhesive-backed foam cushioning. She attaches the sweatband with Velcro so it can be removed and washed. And then she moves on to the back plate. She threads the harness through the back plate to the front of the mask to attach them. The harness is elastic, so it gives the mask some flexibility. And now, it's ready for some ice time. With their various custom paint jobs, these masks all say, "The puck stops here."